Hello and welcome. In this video I'm going to be talking about installing the open source, free and open source EDA toolchain that is called gEDA, gEDA, and the associated PCB editor which is the PCB layout tool that is called pcb-rnd. So what we are going to do is basically download the source code, then compile it and then install it, and then I'll show you how to get it all set up and configured. And we're going to do this both for gEDA as well as for ngspice, which is the simulation engine, and then we are going to do this for pcb-rnd. So let's get going. So of course the first thing we need to do is go find the source code for this project, and to do that all I need to do is go to a browser and search for gEDA, gschem and source code, and that's going to give me the first link is going to take me to the gEDA project, and then I look for this download link here, which takes me to the source code download page. And if I scroll down, of course there's a list of all sorts of packages and all, but I need the source code, so there it is. So that's gEDA GAF stable, which means it's the latest stable version, and there's the tarball. So I'm going to start downloading that, and quite simply just download this entire tarball, and then I'm going to wait for it to finish downloading. And fortunately I've already downloaded this earlier, so I don't really have to wait. So there we go, that's my tarball over here, and all I need to do is, of course I can extract this using the command line, but I'm just going to extract it using the GUI. And now here is my source code. So now in order to begin compiling, first we are going to cd into that directory, and the general process for compiling anything from source is to look at a couple of files. The first one is called the this is the readme file, of course. So the readme gives you all the instructions about what the project is, what it contains, what the new features are, and if there are any installation instructions, sometimes they are here, or and of course in addition there are details about the dependencies, what libraries need to be installed, and so on and so forth. So all of this is fairly important. So when installing a new package from source, it's always a good idea to read through the readme file carefully. Of course I've done it before, and I'm going to skim over all of the material here. We don't really need to look into this in this video, but whenever you download a new source code package and you're trying to compile it from scratch, it's always a good idea to look into the readme file first. The next thing we want to look at, of course, is the installation instructions, which in this case are given as a separate install file. And so if you just open that and scroll down, it's going to give you the basic instructions that we need, which fairly simply are just run these two commands, that is /configure, and after that we need to run make and then make install. So the first command is basically going to configure your system. So that's /configure is going to check whether you have all the dependencies and things like that. The second command is make, which is actually going to be doing the compilation, the building, and then make install actually installs or moves those compiled files into the right place on your system. And so of course detailed instructions are given in this file. Again, whenever you're installing anything from source, it's a good idea to look through this file carefully and see whether any specific instructions need to be followed. So in most cases the install file will also tell you things like options and all, which you need to specify to get a certain feature enabled or disabled. The news file is another useful place to look into if you want to see things like new features added, bugs fixed, new changes to how the software works and things like that. And the file is usually organized in reverse chronological order. So the newest version, the changes are on top, and then as you scroll down you're going to see all the versions below this. So in this case, of course, we are using 1.10.2, which is a minor update over 1.10.1, and you can see there's lots of changes that were made and lots of bugs fixed in 1.10.1. So there's not much new, not a lot has been added since then. So, but we are going to use 10.2 anyway. So let's get started. The first thing to do is to run the /configure command, and when you run this, it's going to go and check whether your all the dependencies are met, whether all the compiler elements are there. So for instance, now it's running. There we go. So that's our first error. It says that we need guile 2.x, at least version 2.0.10, and we don't have that installed. So we need to figure out what package to install or where to get this guile 2.x program so that our dependencies are met. Fortunately, I've already done this installation earlier. So for Ubuntu 20.04, I know which packages need to be installed so that we get this program, this guile 2.x installed, and that happens to be we can install that using the apt-get install command, and then the package name that we need to install for this particular program happens to be this. It's guile-2.2-dev, and in most cases the dependencies are the dev package, meaning development packages, which will contain things like libraries and other header files and whatnot, which you need to be able to compile things from source. So you don't just need the program, you need the dev package for that as well. So now that that's installed, let's run configure again and see what other packages, or if there are any other missing dependencies that we need to install. Okay, so running configure again. Now this time I'm going to go past that guile, but now we have another problem. It says neither libfam nor libgamin development files could be found. So now I need to figure out which package is missing. Again, like I said, I've done this before, so I know which package needs to be installed, and in this case the package is libfam-dev. So again, sudo apt-get install, and that should satisfy that dependency. So now again /configure, and there we go. So now this time hopefully configure should work. There we go. So now the failure is no package python 2 found, right? And that's fairly easy to fix. It's quite obvious. We need to install python 2, and so the package that will give us python 2 again has to be installed, or can be installed just through the standard repository through sudo apt-get install, and the package name happens to be python, I think it's python 2-dev, right? There we go. So again, install, and just wait for it to install, and then we'll run /configure again. So there we go. So configure, and this time it appears that most dependencies should be met. I don't think there's anything else that's remaining. There we go. So now everything has succeeded, and the last few things that you see here is it's been able to create that make file. So the make file is what is used by the next command, which is the make command, and we don't see any other errors, nothing's missing, and so everything successfully checked. Configure has found everything that it needs to be able to build this, and so I think we are good to go. And now the next thing to do is to run make. So just running make is going to basically compile all of the source code that is there, which is essentially going to build all of the source files, and this is going to take a while. Okay, so what I'm going to do is let this run, and just keep an eye on the clock in the top. That should give you an idea of how much time it takes to compile. So all of these messages that are showing up, these are just the verbose messages of what is being compiled, what is actually happening, and most of these really don't make much sense to me as the end user, but for developers who are looking at whether things build, if there are any problems during the build, then we would need to look at these messages and report back to the developers if we run into issues. So as long as we don't get any errors here, we should be fine. So I'm just going to wait for it to finish building everything, and then jump back when it's all done. Okay, so I'm going to pause the recording, and then now it's complete. So you can see it took like 3 or 4 minutes to compile, which may seem like a long time, but really isn't. And the last few things that we see is that make has basically finished building everything. We don't see any errors, and that means everything went well, and we've got all of the compilation has completed. And the last few things that you see is these messages leaving directory, which means basically that everything is completed and it doesn't need to do anything more. So the final thing we need to do is to actually move these compiled files into the right files in your file system, and to do that we need to run sudo make install. Just a quick note here, this command needs to be run as sudo, whereas the earlier commands do not need to be run as sudo, because when we are compiling we are just doing that as a regular user. But when we are installing the files, we need to put these executables into the root file system and make them accessible to all users on the system. That's why this command needs to be run as sudo make install. Basically, we need to run it as root. And so that has succeeded as well. And now we get our these last few messages again that look like that. And then now if I search for gEDA, I have gEDA in my application launcher menu. And now I try to launch it, but nothing's happened. So obviously something's gone down somewhere. And so let's see why it was not able to launch. So I'm going to try launching gEDA using the terminal. And of course gEDA by itself consists of lots of tools. So there's gschem, there's gnetlist, and so on and so forth. So of course I'm talking about gschem, which is the schematic editor. So I'm going to try starting gschem from the command line, and then I get this error, which is some libgeda cairo unable to open or something like that. And that is because this this installation that we did, we've installed lots of new libraries, and the system is not really aware of what new libraries have been installed and where they've been installed and what they are and so on and so forth. So we just need to tell the system to basically go and refresh its database of what libraries are installed, and to do that we just issue this command sudo ld-config, and once this is done the system should know what we've installed, what new libraries we've installed, and it should be able to find that libgeda cairo. So there we go. So all of these messages that you see, this compiling .scm and all this is happening because this is the first time that we are running gschem, and there we go. So gschem is now installed and everything is up and running. The only thing that is missing, or that's potentially an error, is this last message that says can't connect it to FAM, and that is that file, I believe it's called the file alteration monitor, which just keeps an eye on which files have been modified or altered, and I don't think we really need that. I've used gschem without that so far, so we are just going to ignore that. So what we see here on the right side are existing symbols that have come with the default gEDA gschem installation, and so those are all installed. Okay, so now that our gEDA gschem and all is installed, the next thing we need to do is install ngspice, which is the spice simulator. And fortunately the easiest way to do that is to just do apt-get install ngspice, and therefore that's our ngspice installed. Just to check whether everything is installed, just run the command ngspice and we are good to go. Okay, so up next we need to install the PCB tool, which is the PCB layout tool. And what I'm going to do is, all I need to find is the source code, which again I just search for pcb-rnd, and that should take me to the home page of the pcb-rnd project, which is this repo.hu, and I need to find the source code. So under the download section on this page, there's the source code. Now what does R&D stand for? So R&D is basically the research and development sort of branch of PCB. PCB is very much active and existing project under the gEDA umbrella, but a fork sort of diverged from there due to the actions of some developers who wanted to incorporate some new changes, some R&D changes. So all of these on the right is
sort of a list of what R&D stands for and some of the values that the current developers of this branch of PCB try to adhere to. So for my purposes, I found that pcb-rnd was better to use, as opposed to the main PCB branch. Of course, your decision and your mileage may vary based on your usage and your requirements, but pcb-rnd is the better option for me at this point, especially because pcb-rnd supports a lot of import options, especially from things like KiCad and all. And some of our designs, or some of the designs that we need to use, were in KiCad, and so we need to be able to import those and to be able to edit or modify those. So that's one of the major reasons why we are going to pcb-rnd. So to get the source code, go to the download section. The first link is source releases, which is what we want because we're going to build the source. So if you click on the source release, there we go. So the latest version happens to be this 2.3.1, which has been released fairly recently in January of 2021. And the way to get the source code, we can just get the tarball, which is this about 6 megabyte tar file. So it's not very large. We've got the source, and there we go. So I had previously downloaded I think 2.3.0, so it shouldn't be too much different from that. So method is the same. We extract the files. We can do that through the GUI, and then we switch over to terminal, and then we are going to do exactly the same thing as before, which is first go through the readme, the news, and all of those files to understand what needs to be done to be able to compile this or to build this package. But for now, I know that I just need to issue the /configure and then make install, which is pretty much the same as before. The only thing is, internally, of course, pcb-rnd uses a slightly different build system compared to gEDA and all. So the way it looks for dependencies is slightly different. So just looking inside the install file for information, this is the generic installation instruction. So we need to run /configure, as you can see on line number 10, and then it also lists what are the dependencies and what are the files that you actually need to be able to compile pcb-rnd. So the compilation process is pretty much the same as before. /configure is going to run, and it's going to look through all your system libraries, the compiler, and see whether all the dependencies are available. And if everything goes well, at the end you're going to get these couple of warnings that are going to say some things are not available, which may limit some functionality. So in this case we are seeing fun-gw not there. I don't know what that is. lib-f-awk not there. lib-stroke not found. lestiff2 not found. So lestiff2 is of course the older HID, which we don't need, and lib-stroke is for mouse gestures, again, which we don't need. And it so happens that I had installed an earlier version of pcb-rnd on this machine, because of which all the dependencies have already been met. And I just realized this after running this configure command, that I already have all the dependencies. But on a blank Ubuntu system, the dependencies that you will need to install, the packages that you will need to install, are as follows. So I'm going to tell you that in a second. So the packages you need are the first is libgtk 2.0 dev. Next one is this libgtk gle xt1/dev again, and build essential. And in addition, you are going to need this libgd. libgd-dev. So these are the packages that you need to install if you are starting from a blank system, and of course libxml2, again the dev package. So these are the things you need to install if you are starting from a blank or fresh Ubuntu 20.04 installed. Of course I had these installed earlier, and so I don't need to install them at all. And so when you do /configure, it should run and succeed at finding all the required dependencies, and you should not get anything missing. So like I said before, the first warning is about fun-GW, which is for something to do with scripting, and I don't think I'm going to need any scripting right now. I'm just going to use the GUI for most purposes. And of course, as I recall, fun-GW is not even available as a deb package yet. The second one is for mouse gestures, which again I don't use, and that's the lip stroke library that's not found again, and most people don't need it, and I've definitely never used it before, and so I don't think I need it at this point. And lestiff2, the last one, is the HID, which is the human interface component, which is an older HID system, which again is not being used, so we don't really need that, and we are just going to be using the available HID. So just make sure that at least one HID is available. And so now, since configuration is complete, I am going to run the make command and /make, or just make, sorry, not /make, just make. And again, compilation is complete. Again, you can see the wall clock. It took a little bit longer than what is the recorded duration here. And then once that's done, all I need to do is sudo make install, and that installs all the files in the right directories in my system file system. So now, just to start up PCB, I say pcb-rnd on the terminal. There we go. And to check which version we've got, click about, and there we have it. So 2.3.1. Looking at our source code, that's what we had installed, right? So 2.3.1, that's what we've got. So that's about PCB. So I'll just close PCB for now, and then now let's get to configuring all these tools up so they're ready to use. So the first thing we need to do is to understand the configuration, or how do I tell gschem and all the associated tools where my symbols are kept, where my footprints are kept, and so on and so forth. So let's begin with that. Okay, so just a quick introduction and sort of background. Gschem and all the other tools that are under this gEDA family, they all follow the Unix philosophy of being independent tools that work well together. So which means that as tools they are fairly independent. The implementations, how they work, is developed sort of independently, but they adhere to common standards for input and output file formats, for interfaces and things like that, which allows an end user to use all of these tools together, but also allows the end user to use any other tool in place of one of them. For instance, if you don't like gschem as your schematic editor, you should potentially be able to use something else. If you don't like gnetlist as your netlister, you should be able to use something else, and so on. So in that sense, all of these tools, so for instance, gnetlist, gschem, all of these form a family of tools. They are all called gEDA and friends. And of course, there's a loose definition of and friends, which includes gschem, gnetlist, and so on and so forth, but also includes things that work with these tools, like for instance, like ngspice or PCB, and so on and so forth, right? So the first thing to know is that GAF, the word GAF, gEDA and friends, refers to all of these tools in this sort of family of tools. So GAF refers to gnetlist, gsimcheck, gschem, and so on and so forth. There are lots of various tools, and there used to be this GFCH to PCB, XGSCH to PCB. So lots of different programs actually use this term GAF. Now GAFRC is the configuration file for all tools that are in the GAF family, gEDA and friends family. RC stands for I believe some kind of a configuration file. So if you find a file that is GAFRC, then that's for all gEDA tools, gEDA and friends tools. Gnetlist RC is only for gnetlist, gschem RC is only for gschem, right? So whenever you launch one of these tools, for instance, if you launch gschem, it's going to look for a GAFRC, and it's also going to look for a gnetlist for gschem RC. So where are these files kept? Of course, the system files are in this particular directory, and they are called system-gafrc system gschem-RC, system gnetlist-RC, system gAttrib-RC. gAttrib is another tool in this gEDA and friends family, and so on and so forth, right? So the first configuration file that the tool is going to look at is going to be the system gaf-rc, because that applies to all tools in the GAF family. So for instance, if you launch gschem, it's first going to look at system gaf-rc, then it's going to look at the system gschem-rc, right? gnetlist, for instance, is going to look at gaf-rc, and then it's going to look at gnetlist-rc. So if you want any commands, or if you want any configuration for all tools, you should put it in gaf-rc. If you want any specific commands for gnetlist, you should put it in the gnetlist-rc file. So that's how these RC files work. So these files are the global files. Now on a per user basis, you can put these files in your home/.gEDA folder, and any files in this folder are only going to be read by programs when they are being run as this particular user, right? So I happen to have a couple of example files, so I'm going to bring those in and put them here. So the first file is actually not a gschem file. It happens to be this file called gschem-ICQ colors, which is basically a color definition file. So all I have to do is copy it here, and just to tell you what that color definition file does, if you launch gschem, it comes up with this black background and white text on top, which is the default, but I happen to not like it a lot. So I want this light color scheme, which you can select manually after you start it, but even that is not too great. So I happen to find a new color definition file, which is this gschem-ICQ colors, which I want to use. So here you can see that lots of things are defined. Background color is defined, pin color is defined, maybe graphic items, net, and all these things are defined in terms of what color they should be. And this is a nice color scheme, and I like it, and I'd like to use it. So first of all, we need the definitions of those colors. So that's that file there. And now I need to tell gschem to use this file, right? So let's go and put that. So now I've pasted in a file called gschem-rc, which essentially contains this. So just a quick note, this gschem is in the language scheme, and anything that begins with a semicolon, as you see up front here, that's a comment. Okay, so anything that begins with a semicolon is going to be ignored, and all statements or all commands or all configuration lines are essentially in the format of open parenthesis, some command, then some parameter, and then close parenthesis. So for instance, the first thing that you see is the load color scheme. So let's uncomment the second one, and let me point it to the correct location. So I need to point it to I need to tell it to look and pick up this gschem-ICQ colors. So the second line is what I'm going to change right now, and I'm going to make it point to the correct path. So that happens to be /home/kabjit/.geda/file name, which is gschem-ICQ colors. So now this second line is uncommented, and the last line I'm going to keep commented for now, and I've saved that file. Now let's start up gschem again and see whether that's taken effect. So there we go. So now I've got this light color scheme by default, which I happen to like much more than the default black background scheme. It's just much easier to read, so you can see all the pin colors and all taking effect. So there we go. So then coming back to the gschem-rc, the last line that is there, this is from an older system that I used to have, where I didn't want the window size to be the default. So I had added that in. Depending on what size monitor, what kind of display you're using, you may need it. At this point, I don't think I need it, so I'm going to leave this this line entirely commented out. And depending on, of course, your display system, you may need to uncomment this and set it to some default value. Okay, so now starting up gschem again, what we see now is that on the right here are some default symbols and default libraries that are available. So when we install gschem, let me just expand that, we get some symbols by default. So these are lots of nice symbols, and of course they may not be enough. We may need to add more, may need to create more. And so the next part is we need to figure out where should we place these symbols that we either create ourselves or we get from other users or collaborators. And we need to get these symbols and store them in a certain specified locations, and then we need to tell, of course, gschem and all the other associated tools where to find these symbols. And so the standard way of doing that, or rather the convention that I follow at least, is to have a directory called gaf in my home directory, which is going to contain all my gEDA, gschem, and all these EDA files. And so first I'm going to create this directory called ~gaf, inside which I'm going to store all my files, and under this I'm going to have three broad directories. So all of the stuff that I create is going to go under here. The first one is going to be a projects directory that's going to contain schematics, that's going to contain layouts, whatever. So every project, it could contain simulation models, whatever, but everything is going to be under that projects. Then the second is going to be a symbols directory, which is going to contain circuit symbols and things like that. And the third is going to be a footprints directory, under which I'm going to save PCB footprints and pieces of layout and all of those things. So that's going to be my third directory. This is just a standard workflow or standard setup that I use. It's just convenient to have the standard setup, because if I move machines or if I have to share files and things like that, then it's okay. Of course, one thing is having these symbols and footprints in one place in the user directory means that when you share a project, you have to be careful to share the symbols that are required for a project as well. Of course, there are scripts that will automatically pick up these symbols and pick up the footprints and share them, but we need to remember to do that. The other advantages of having these symbols and footprints directory is that once you create a symbol, it is available across all projects. If you find a bug, you have to improve a symbol or you have to fix something, then once you make that change, it's available to all projects that you're working on. So that way it's a little bit easier rather than having a per project directory. So now we need to tell gaf, gEDA and friends, all the tools, where these symbols are, and so I'm going to do that here. So these first few lines are the old locations from an earlier machine, earlier configuration that I used to have, and I don't need that right now. So in general, the component library is the command that tells gEDA and friends where the symbols are kept. So every line is going to point to one directory, and this last line that you see, source library, it refers to things like spice models, spice subcircuits, and spice definitions, again, which I don't have right now, but if you have them, you could create another directory in your gaf folder called spice data and add those in. Again, as you can see, most of these lines are commented out right now. So right now we have only one folder, so let's go and fix that, and we'll add the first symbols directory to our gaf-rc configuration file. So first we need to check what the path is. So that path happens to be /home/ your username /gf. So let's go fix that in this gaf-rc file. So all you need to do is, for now, that's the correct path, and then add this and followed by the word symbols, and that's it. So now once you save this, and make sure to uncomment this line, which means to remove the semicolon at the head, and make sure that the path is enclosed in double quotes, and that's it. So now if I start up gschem, I should see my symbols directory listed under my libraries tab on the right. So let's try that. Okay, so of course there are no symbols there, so there's nothing under there. So let me copy paste a symbol that I already have, and this is this psoc v2 symbol. So I've copied that into my symbols directory, and now what I want to see is whether gschem is able to recognize the fact that I've added this symbol in here. So all I have to do is go and refresh my folder, refresh the libraries tab, and there we go. So now I'm able to see this psoc v2 symbol, which happens to be the symbol for a programmable system on chip IC microcontroller from Cypress Semiconductor that I used a long time back. One thing to note here is that the path to the symbols directory must always be the folder that contains the symbol. So the symbol must be inside the folder that your component directory is pointing to. So if I don't have, if I have folder inside folder, or hierarchical type this one, that's not going to work. So what I've done is, just to demonstrate that fact, I've got these two directories, 1 and 2, and I've put two symbols in each of these. And if I refresh now, there are no symbols inside the symbols directory, so it shows up as blank. And so the way to fix that is to individually point my gaf-rc to the two folders that I've just created, and have them point exactly to where the symbols are located. So if I go back to my, so for instance, this is the first one. So if I go back to my gaf-rc, there we go. So now if I open my gaf-rc, now I need to add the exact subdirectory of the symbols directory. So that's dev1, and that's the first one, and I'm going to just copy paste that and dev2 in the second line. So now I can save that. The only thing is, once this is saved, now I've got two component libraries, dev1 and dev2. As you can see, the dev1 contains one symbol, dev2 contains the other symbol, and that's it. So now I need to quit and restart gschem for the new configuration file to take effect. I just make sure it's saved, and once I start gschem, there we go. So now I can see dev1 and dev2 folders, each showing one symbol each. So this atmega32 symbol, by the way, I got it out of, I believe, the gEDA symbols.org repository a long time back, and that's the symbol for the atmega32. And so you can see who the author is and so on and so forth. This is just for an example, and the psoc2 symbol is something I built, or I created a long time back. So there we go. So that's how you create symbol libraries, and how you tell gEDA and gschem and all the other tools where to find symbols that you have created or you have obtained from elsewhere. So that's about how to set up the gaf-rc or the library locations. Okay, so the next thing is, there's this niggling error about this canberra-gtk module that seems to be appearing for some reason. So let's go and see if we can fix that. So the easiest way is to figure out what is the missing library and what is the package that I need to install in order to get rid of that error. So I happen to know in this case that to get rid of that, I need to install this, I think it's called lib-canberra. So there you see what you see on the screen, lib-canberra-gtk-module, and installing that is again just a matter of doing the right sudo apt-get install, and once that is done, hopefully our that previous error should go away. So let's try gschem, and there we are. So now no more lib-canberra error. So that's sorted out. Okay, so the next thing we need to do is to get some symbols, and one of the best resources for finding circuit symbols and of course footprints is the online repository called gedasymbols.org. So on the right here you can see a number of authors. Of course my name is here as well, and one of the easiest ways to find these symbols is just to go here and download, or you can download the whole site via CVS as well. And there are multiple authors on the right. You can see them all listed. You can just select one of them, for instance, and then you can see there are lots of symbols, capacitors, connectors, crystals, diodes, and so on and so forth. And if you scroll all the way down, for instance, the footprint should be listed right at the bottom. So let's see if we can find those. Yeah, so these are symbols, and then footprints are, there we go. So these are the footprints. So lots of different kinds of footprints for capacitors, connectors, diodes, and so on and so forth. So when you need a connector, all you need to do is look at gedasymbols.org and see if what you need is there. But even before that, what we need to do is find some PCB footprints, and the easiest way to do that is to look for the pcb-rnd footprint library. So the corresponding thing, that is the repository hosted by pcb-rnd, is called edakrill, and it's sort of a okay, so this is not the right page. There we go. So it's called edakrill, and the best part about pcb-rnd is that it enables you to pick up footprints on the fly. So let me see if I can find the link for that on the main page of pcb-rnd. There we go, web footprints. Yeah, these are instructions on how to use the plugin to fetch footprints from edakrill. So edakrill is like is sort of an equivalent of gEDA symbols, and pcb-rnd has a plugin that requires or enables you to fetch footprints on demand. So you don't have to have all of them saved. You can pick as and when you need them. And so edakrill works pretty much the same way. You can search for a footprint that you need, and for instance we can do a parametric search. In this case, let me just put my name as a filter, and this should show up. This should give me a couple of footprints that I have created. So scroll down. There we go. So this is one of the footprints I created for the PSOC 5 programmable system on chip microcontroller, and so you can download it as a tarball, and that's going to be the symbol file, and you can get that. So this is a nice resource, a nice place where you can get both symbols and footprints. And the plugin fp_wget, again I'm not going to go into the details at this point, but this plugin allows you to fetch footprints from that library, that edakrill library, as well as gEDA symbols from the cloud, without needing to have everything saved on your local machine all the time. The only downside, of course, is that you need an internet connection, which means that you can only fetch when you are connected to the internet. So that's one bonus of having this live fetch type system. Okay, so we need some footprints now. We've got lots of symbols. What I want to do is look for a symbol repository that has been created by John Luciani. So if you go here, I believe that there's been some change in the domain name, because of which the links on the gEDA symbols page have broken. But if I just do a quick search for Luciani footprints, I should be able to find the new domain and the new website where it's moved. So there we go. Yeah, Luciani family, PCB footprints, and then all I need to do is download this this tarball PCB symbols -jcl .tgz, and that's basically your tar file that contains a huge number of symbols. So let's take a look at this file. If I extract this file, and I'm not going to extract it here because I've already created a footprint directory, so I'm going to paste in that tar file here and then extract it here. And so once I extract it, you can see that inside it is this huge number of footprints, and so they're varying types. Most of them have some sort of a descriptive name. And to see these, now we need to tell, now that we've got all the footprints here, let me just rename that folder to Luciani, and then I can remove this tar file. I don't need this tar file sitting here anymore. There we go. So now all these footprints are sitting inside this folder. So now I need to tell pcb-rnd where to find these footprints. So let's go do that. So let's launch pcb-rnd. Now we've the way to look at it is you go window library, and now these are the footprints that are distributed by default. These are the footprints that come with PCB, and of course we have some surface mount, we have some through hole, And the interesting ones are these parametric footprints. So for instance, if you look at this dip footprint, this requires a parameter. So for instance, right now it has a certain number of pins, but you can go and change that. So let's say you want a 4-pin dip footprint, just type in 4. Dip 4 will give you a 4-pin dip. If you want, let's say, an 8-pin, okay, so just a typo there. So if you want, let's say, 8-pin, there you go. So now you can get an 8-pin footprint. If you want anything more, you can put it in there. So for instance, a 20-pin. And of course, other parameters can also be changed. For instance, clearance, ring dia. If you want some other parameters to be changed. I haven't really played around with these so far, so I'm really not sure what the parameters are and what they do. Okay, so the next thing is, of course, to tell PCB where it can find these footprints that we have just downloaded. So the way to do that is go to the library setting, and what I need to do here is to add the location, and what the options that we have are user, design, and so on. So when I select user, it means that all the configuration additions that I'm going to do are going to be for the particular user, so that's me. So for all projects, and so all I have to do is insert before, and then I'm going to copy the path to these footprints. So I can do copy and paste here, and therefore, and thereby enter this. So there we go. So that's it. And you can click on the help and see there are some variables, dollar variables that allow you to use computable paths, but of course I'm not going to be using that for now. I'm just going to hard code my path to the PCB footprints directory that I've just downloaded. So I don't need this, so I can close that, and I've entered the path up there. I can say OK and then close. So there we are. That's the library that has been configured, and because it's right on top, that means that's the first path that's going to be checked whenever I look for footprints. So I'm just going to restart PCB to make sure that the change I made has taken effect. So there we go. So pcb-rnd, going back to the library view, or basically preferences first, then library settings, and there we are. So my footprints configuration is there, and then we go to the library to check whether I can see all the footprints. So there we go. So now I can see that library, and I can see all the footprints within it. So there we go. So now when I want to use a particular footprint in my design, all I need to do is, for instance, 0402 or whichever footprint I want, all I need to know is the name. That is the footprint name. And if I copy that name into my schematic file, then that's how my schematic editor knows what footprint is to be used when I do the layout. So here there are a variety of footprints, all the way ranging from SMD all the way to through hole, as you can see here, and the footprint name is just this entire long string. So of course there's no easy way to copy this. You need to basically just type it out, and for some of the longer ones, it may be easier to just go to your directory, look up the name, and then copy paste from the file name, and then put it into your schematic. So variety of footprints there. This is like the largest single source that I know of for footprints that are open source and all. But of course, once you start making your own footprints, you'll have to add them to a library, and then add the library location in PCB like I did just now. So that's pretty much it. So that's the end of this tutorial. I've covered everything from installing gEDA, PCB, and ngspice, all the way to configuring it, downloading some symbols and footprints, and in the next video I hope to cover creation of symbols and footprints, and then we'll take it from there.